Moji will then do a more of a deep dive, and then of course we'll open the floor. I mean, this is a community of practice, so this is not about necessarily us getting on our high horses and talking about things. This is a engagement for the community as a community of practice. It'll be really good to have some discussions as well. Next slide, please, Moji. So just before we get to, maybe I mixed up the slides, I might do acknowledgement of country. I would like to acknowledge the traditional owners on the lands that I'm on. I mean, I'm actually in Melbourne, so it's not my home community is different, but here in Melbourne, I'm in the suburb called Narre Warren, and I acknowledge the Bunurong and the Wurundjeri people and of the Kulin Nation, and pay my respects to elders past, present, and emerging. And certainly, regardless of what technology we're talking about, obviously, myself and many of you in the room are, I'm sure, passionate advocates for having a material impact in closing the gap for our First Nations people. So just really quickly, for those of you who don't know, QCIF is a not-for-profit organization, and we are obviously looking at cutting edge and data and digital capabilities. We do a lot of training, and we're hoping to build, contribute to the next, the emerging future researchers and innovators in Australia and beyond. And also, we play a role in catalyzing a lot of partnerships, both within Australia and with international peers. The reality is QCIF could never do any of this without many, many partners and collaborators, and that is reflected in some of the work that we'll talk about today, especially what Moji is going to talk about. We do work with hundreds of projects, and that's super exciting and really rewarding. But obviously, like many of us, we would love to do more, but constrained by Australia's funding and research and development environment. Next slide, please. Moji? Yeah, thanks. So just a little bit more of a dive. So these are the kind of different areas that QCIF is involved in. And you see that the quantum and AI, we've actually deliberately lumped it together. And that's because most of this kind of area is looked after by Moji with the help of many of colleagues both within and outside of QCIF. But it is certainly an area that we're working in both with university academic partners and hopefully also moving into some of our partnerships with, for example, with PsiQuantum. Next slide, please, Moji. Here are some of the partners, and a quick slide just to say that we don't do this alone. We work with many of the partners, including, of course, ARDC and many of the NCRIS capabilities as well. Next slide, Moji. All right, so first of all, I think it's really important to understand when we talk about quantum, from a government policy point of view, this is not about necessarily just about quantum computing. What we're really talking about here is building a new industry for Australia. And, people have talked about quite a heavy investment, especially considering our constrained funding environment, that for the PsiQuantum to get them onshore in Queensland and Brisbane specifically, it's heading into $1 billion, right? To get them here to set up shop and manufacturing essentially within Queensland. Moreover, the Queensland government has contributed to that, and also most recently, I think actually on Wednesday, the Queensland government's investment with the University of Queensland and many partners is kind of opening up the very first kind of open access quantum test bed, for example. So there's a huge amount of investment, but why Australia, and from a Commonwealth and state level investment, why we're doing this? So the reality is Australia as an economy, we are a one-trick pony. We are essentially a resources sector-based economy. There are some exceptions, for example, international students and what education that we export. But predominantly, we are a one-trick pony. Like we put all our eggs in one basket, if you like. Um, Things that we dig out of the ground, some would argue, and for those who pay attention to politics, will know that, we, even within that sector, are probably not deriving the full value of what the country could garner. I mean, for those of you who follow Dave Pocock will know about conversations around taxing gas, for example, the export of gas and so on. But more broadly now, when you think about quantum, what we're really talking about is bringing a new industry where Australia can immediately derive some dividends by being first in a global market context. Of course, we'll always compete with the other more, other developed countries in Europe and in the US. But in saying that, we have punched above our weight when it comes to quantum technologies and quantum computing. So the idea really here is if PsiQuantum is considered sort of the anchor, you want to build a whole community of small, medium enterprises around that quantum industry. But it's not enough to think about where we've come from, which is really being driven by passionate advocates like Kathy Foley, the former chief scientist around quantum opportunities. But when you're thinking about an industry and well beyond research, it can't just be about quantum physicists. In order to create an industry, you need lots of skilled and varied, highly skilled workforce to be actually, to build an industry around this. And this is, again, it's not just about the research and academia, the PhD graduates. This is also about all the other ancillary workforce, skilled workforce you need to create an industry. And this could include things like, people who look after cryogenics. Cryogenics in a quantum computing context is very different to people going and servicing domestic or commercial air conditioning. But do we have that workforce to do that? More applicable is not more applicable, but similarly, how do we, quantum computer that has sufficient qubits might be a little bit, further away than we would like, but at the same time, if you can't code in a particular way and think about some of the applications and doing some prototyping around what quantum could do into the future, unless we train our new graduates about coding in quantum environments, whether even if using kind of quantum emulators, then who cares that we have quantum computers if there's no applications, right? So I think we've got to start thinking about those applications now, rather than waiting for the 1,000 qubit or beyond computing capabilities. I think I won't talk too much about the AI and quantum convergence. I'll leave that to Moji, but that is also an immediate opportunity right now that we can explore and are exploring to make quantum real. Next slide, please, Moji. So just focusing on the skilled workforce, we do have a project with the Queensland government that Danny Melancello is leading from QCIF. It's about we've called it kind of catalyzing vocational and higher education skills continuum for quantum career pathways. Or in other words, this is actually what it's saying is that can we think about a workforce for quantum that is more than just about higher education and universities, but it's a continuum of also inclusive of also the TAFE students as well and their skill sets. So this project was funded by the Queensland government. Next slide, Moji, thanks. And the project's objectives is really, look, you think it's difficult to change courses and course content in universities. It's even more difficult in the TAFE sector, in the vocational sector. So what we try to do is, in this project, it's a 3-year project funded by the Department of environment, let's see, science, tourism, and innovation, or any combination of those words. And what we're trying to do is to bring and expose TAFE Queensland students from different programs into quantum opportunities. And you got to remember, a lot of the quantum opportunities are not just about quantum computing. Quantum technologies include sensors, um, sensors, optics, many other facets of quantum technologies are actually happening right now, and a lot of the research infrastructure facilities, like the Australian nanofabrication facilities in the NCRES community, are a large part of that equation. So these are sort of our objectives, but at the same time, we were kind of learning on the go because we didn't quite understand how the vocational sector works. So there's a lot of learnings through this project, and we're only really into the second year within a 3-year kind of program. Next slide, please, Margie. So one of the pilot programs we did was a very limited number of students, but we wanted to understand what would it take to take TAFE Queensland students through a really intensive program in if you like, in the flavor of quantum technology. So the natural partner here was the Australian nanofabrication facilities, specifically the Queensland node. And we did sort of a 6-week program where they were thrown into the mix of some of the quantum technology. Don't forget also, in most cases, the TAFE student cohorts are, many of them are 15, 16-year-olds. So this is really early exposure to quantum technologies. We went through this program, and now we learned a lot from this initial kind of pilot program. Next slide, please, Moji. So our next approach to this is a tiered model, and this is what we're working through and in some cases implementing, because to do a completely immersive option is really costly, first of all, not in terms of necessarily dollars per se, but time and effort it takes to do it. And there are also many kind of challenges that we face, things like work cover, things that you don't really think about, but are real considerations. Work cover, insurance, liability, all these kind of things became things that we needed to solve through that project as we were delivering it. So we come up with a multi-tiered approach, which we're in the middle of deploying, which is everything from kind of low intensity, light touch supervision and kind of hand-holded demonstrations and exposure to shadowing to all the way to tier 3, like what we did with ANFF. But we wanted to have a more tiered approach so that we could cover a larger cohort of TAFE Queensland students to give them experience in quantum technologies. And the reason why we're doing it, if I go back to the project exposure, is that we want TAFE Queensland and other vocational providers to think about that future. Because again, I go to the point, what we don't want to do as a country is invest $1 billion in bringing an anchor tenant, and the anchor tenant saying in 5 years' time, we're ready for our computer, but you haven't provided us with the workforce to keep an industry going. We're moving offshore. That is the risk, the real risk that we want to try to mitigate now and build a pipeline of talent now so that when the computers are ready, that we actually have a workforce that can meet the demand, both technically and in terms of capacity of enough people being able to deliver on the quantum promise. Next slide, please, Moji. A little bit more details about the program itself. So we've got kind of 2 pathways. One area we're looking at is more general lab skills and lab techniques, certificate 3 and 4, but also we have a more specific targeted quantum area around cryptography that Moji will touch on, and he'll highlight why that's a priority area. especially in the fintech and the financial sector. So it's a more targeted approach. So it's very much in the data and digital space and cryptography and that we're exploring as well. Next slide, Margie. And of course, finally, to round things off, this is all has to be connected back to national policy. For those of you, I'm sure all of you, if you're not aware, should know about the Ambitious Australia report and its now implementation. Obviously, the whole idea around vocational to industry workforce model is captured within Ambitious Australia. So very much our work here is very much aligned with that. Of course, the Ambitious Australia is only just starting to be implemented, the recommendations that are coming out of it. But of course, it's always nice to have programs running that are aligned with national policy. I will pause there. So this is a really high level kind of snapshot about the macro view of quantum technologies and where the state of affairs, if you like, at a very high level. I will pause there and open the floor up if people have questions or comments for that matter, because people have different opinions about the prospects of quantum and quantum technologies or quantum computing specifically. So I'll pause there and open the floor. If there are no questions or comments, of course, we can move on. Sorry, I can't see everybody. Is that Ilan?
Hi, Sach. Ilan here from ARDC. So great to hear about this project. I wondered, Sach, if you could comment on quantum literacy starting in primary school and and whether QCIF has been doing any work in that space, or are you aware of other partners? I'm very familiar with when Queensland's quantum strategy was released, seeing the workforce capability element embedded in that was really exciting. Yeah.
Yeah, look, I think the Queensland government's program is actually the broad program name is called the Quantum Academy. And I think within the academy there is certainly secondary school-based, if you like, again, early exposure to quantum technology. So it is in fact going right into secondary school at least. I'm not sure about primary school, but secondary school certainly. So I think the government, certainly the Queensland government's of the view that, again, I think they are acutely cognizant of the risk that if they don't have this workforce ready, PsiQuantum and for that matter, any other supporting SMEs around that anchor tenant could disappear if the workforce isn't there. Because that's a really easy excuse for a big multinational company to say, you don't have the workforce, we're off.
Yeah. And Sach, are there any additional learnings that we could take from, the success of the biotechnology industry and investment that we've had in Queensland, and I guess any learnings that we could transfer?
Yeah, look, it's interesting, isn't it? Because Queensland made huge step changes with all the capital investments that were made through the Smart State program. And I think a lot of the biotechnology industry was built on the back of that heavy investment. And I guess Queensland was also strategic and, a little bit of luck as well in that Chuck Feeney came to the party with Atlantic Philanthropy and donated huge amounts of money to the Queensland effort. So it was a little bit of good strategic insights and clever investments. But I can only speak to even like when I worked for QUT. If you think about QUT's journey with the Chuck Feeney investment, it went from a university that just became a university from a technical college with a very modest research profile to now, $110 million Herdic return, for example. But that kind of jumping from like 30, 40 million to 100 plus wouldn't have happened without that investment. And that goes beyond biotechnology, of course, but it's just case in point about you can build it, they will come, but you have to also then wrap around that support structures. And some of the support structures in that particular example was investing in research infrastructure, actually. And that research infrastructure included things like, the equipment but also the people. It was a very deliberate strategy to recruit research infrastructure people as well. People who are experts in electron microscopy, people who are experts in, genomics and omics, and for example. So obviously things like omics capabilities were instrumental for the biotechnology industry, right? And some of the successes of microbia and others in Queensland. Yeah.
Yeah, and it's exciting. Final comment, exciting to see where the intersection between our burgeoning quantum ecosystem and the biotech industry is
Absolutely.
going to converge. Yeah, anyway, enough from me.
Who was next? Sorry, there's a few hands up.
We've got Jack for you.
Go ahead, Jack.
Yep. Hi there. Thank you very much for that. Very exciting and very interesting. I guess my question is similar to Ilan's, which is in addition to sort of training up the workforce from a certain level, say, let's say TAFE now, what are thoughts on people transitioning from other industries? So Australia has a very educated population in all kinds of things, but not necessarily, I would say quantum physics is, one of the rarer things out there. Is there some sort of thought on people retraining into it if they're already, let's say, masters in something else, postgraduate in something else?
Yeah, interesting question. I think part of the challenge, of course, is that, if you think about sort of quantum theory and quantum physics, so this is more direct roles in the quantum technology industry. I mean, Australia has to be a little bit careful because there's so many people moving away from fundamental mathematics, for example, right? And we have to deal with that at school age. So in some ways, the retraining, highly educated and retraining is feasible, but it needs to be underpinned by kind of a good understanding of the mathematics, the fundamentals. On the other side, of course, what I call the kind of ancillary support. So people who do really sophisticated welding and people who do cryogenics, people who do, when I say plumbing, I'm talking about different types of plumbing. So if you think about the traditional tradie path in TAFE, they can certainly be retrained to deal with high pressure vacuum and more, to support an industry. They are definitely ready to be retrained or given the opportunity to be specialist trained, be specialists in kind of quantum related technologies because, most of the HVAC TAFE courses are all geared towards domestic and commercial markets. But if we have an industry in quantum, they could specialize in dealing with, hydrogen and so on, helium cooling and blah, blah, blah. So there is definitely potential for retraining there. But I think in terms of the, quantum physics kind of related jobs, we probably do have to deal with some of the skills gaps in mathematics that the country seems to be facing at the moment.
Yeah, super interesting. Thank you.
All right, thanks. Nana? I think it was Nana next, was it?
Yeah, it's Nana
Yeah.
next.
Sure.
Then we might wrap up and continue on with the next part of the presentation after that, Nana.
Sure. So I would, this is an exciting topic, and I would like your take on, the uncertainty surrounding this. That is, while quantum offers long-term promises, but at the same time, it is both timing and the scope remain uncertain. And how should you approach this? And as such, we know, excuse me for saying this, Australia has always been risk averse in its technological investments. And that too, if it gets burned a bit early, then it shies away for too long. And
Yeah.
so is there a measured approach to this?
Look, no, I think, I mean, again, digress a little bit. We do have problems with our political system, the Westminster system of two parties, 3-year cycles, and, quite fickle in their
Yes.
policy making. Let's put that to the side. And I did notice that Kathy Foley did publish something recently in, I think, Innovation Australia about saying, you know, hold tight, just be patient around quantum. So I think the fact that she had to say something like that tells me that, there are naysayers and people who might think this is a waste of time. Let's be honest. There is um, certain parts of the ecosystem who have doubts about quantum's utility moving forward. But I will also say that people can learn from history, right? I mean, AI has been around for many, many years,
Yeah.
decades and decades, and it didn't necessarily deliver on its promise then. There was a bit of a pause and maybe a few backward steps. But when the hardware caught up, all of a sudden it all accelerated really rapidly. So we shouldn't lose sight of history, lessons from history, that sometimes there are pauses, you might have to wait, but doesn't mean all the work that was done was wasted. It just came to fruition later. So we have to be careful that um, I think the only thing we can do now to answer your question is we should remind people of that historical context, that there are industries that are booming now that had a little bit of hiccups along the way.
Yes.
Thanks.
Yeah. So yeah, thank you. I mean, yeah, that is keeping that in mind. It's a wise advice. Yeah. Thank you.
Okay, I think I'll hand over to Moji now. Thanks, Moji.
Sorry. Thanks, Ash, for the great overview. I might have to share again because for me, it came out of full screen, which is a bit distracting. I'll quickly try to do that. Sorry. All right. Yep. So Sash had for us a great overview of what's happening in Australia, what we need to support that industry. I go a little bit more into the details with technical outcome reporting, not technical method reporting, to show you like where there are promises and where it is going. Get to my own slide. A tiny bit about myself. I did my PhD at Griffith University. Was experimental quantum computing with trapped ion. We did it with Georgia Tech in the US and Fraunhofer in Germany. Then I also worked as a senior data scientist / postdoc at UQ, applying AI to quantum machines and applying AI to health datasets. A bit of detour in Queensland Treasury emission modeling, and then it's been a great year at QSIF as a head of AI and quantum algorithm. And yeah, we are trying to see where it really can, both AI and quantum can help researchers and create impact. I also run this meetup, Quantum Computing Australia meetup. It's on Meetup website, and QSIF is now a sponsor, and we are doing joint meetup with Quantum Australia. It is live streams. We have a few meetings a year, and then we summarize where the quantum industry is now and where are the applications. So it's for mainly for non-quantum experts and focusing on application. So if you like to, you can stay in conversation. That's one way of joining. Okay, this is how I arrange my talk. You start from where quantum computing is today, and then we focus a bit on quantum machine learning, where is evidence, where is promise, and a bit better focus on where the signal is real, means that we are seeing a difference actually rather than hype. Then we go to quantum security, post-quantum cryptography, to be exact, and a bit of a detour to a relevant project that we are doing, federated learning, and I tell you how it is relevant to post-quantum cryptography, and then in general where Australia is heading. Okay, where are we today? So I don't have much time. I usually start with what is quantum computing. Let me give you an introduction, 2 minutes before I jump into this. So you have normal computers, 0 and 1. You do like adding, multiplying, differencing. On top of on a CPU. On top of that, you can build very complicated algorithms, and you can do great things. With quantum computing, you are actually saving that data on quantum objects. This can be a photon, this can be an atom, something like that. And when you do that, laws of quantum mechanics lets you have them in between 0 and 1, and then match them, pair them with other bits, which gives you, it is called entanglement. And these two capabilities can give you a huge space, a lot of numbers with like very complicated ways of manipulating them. And it can be harnessed to do things that no supercomputers can do. But what do we have now? Let's say, for example, IBM has like 400 qubits, also 1000 qubits, superconducting quantum computer. Is 400 qubits is working better than 1000 because the noise goes so high that the number of faults goes up, and then it cannot do better than the 400 one. So that's the problem. We have a lot of noise. We need to fix that. That's mainly a technical challenge rather than basic scientific challenge, but it's a very hard technical challenge. And when we reduce that noise, like noise meaning you try to save some number or do some kind of operation, it doesn't do what you want. If we reduce that to like 0.001, let's say, then we can add to that fault tolerance, which is you use a lot more number of qubits, and then if some of them fail, you can compensate for that with the extra ones that you have. Meaning from the outside, you can simulate perfect quantum operations. We don't have that yet. PsiQuantum is heading for that. Their roadmap 5 years, I would say like 7, 8, 9 years, based on my own experience, but we get there. It's how much money you put on it, how many people you put on it. It's a technical challenge rather than a basic theoretical hurdle that you can never pass. And another problem, data loading. You have some numbers on a normal computers. You want to just put it on a quantum computer to start operation. It can be really slow. People are working on that as well. And for now, advantage is domain specific. Not even domain specific. When I say domain, I don't mean like broader domain. It is being trialed in transport, but in many cases, it still cannot do anything. In some very narrow problems, specific problems, people have shown that this can shows results on smaller data sets that kind of proves that if we can apply it to the larger data set, it will do much better than supercomputers. Why can't apply it to bigger data sets? Because you need a bigger quantum computer. You need like a 1 million qubit, let's say, something like that, that again, Psi Quantum is aiming for directly. But at this point, numbers are low, noise is high. So a lot of work is like simulation, and that basically with that you can go like 30 qubits, means that if you're doing bus scheduling, you can do 30 buses, not 150 that you really need for Brisbane, let's say. Yeah. So where's promise and yeah, where's the actual outcome? I need to make this clear that the first few slides that you see might come across as very negative. What they're doing is de-hyping what we have now. So it's not, at this point, we don't have algorithms that can do so good in very practical applications that beat supercomputers. That's the only thing that these slides are conveying, but it doesn't mean that we cannot do that in 5 years or 10 years or something like that. It is waiting for the hardware mainly, and also algorithms. People are hardly working on making new algorithms, making the current algorithms better. So the theory for many applications is already there. We just need better devices, and some others we need to create better algorithms as well. Now, one result, for example, showed a peer-reviewed paper showed that, sorry, a review paper showed that in many of peer-reviewed papers on quantum algorithms, a simple logistic regression, which is basically sort of the simplest model that we have classically, 3 out of 5 they can easily beat a quantum machine learning model. And then if you basically sit on it and use much more complex one, you can beat in every case you can beat a quantum algorithm. Except for some narrow cases now, it will be a lot better in the future. But still now also, I will show you some result where quantum computer is beating classical. It's narrow, but we have it today as well. So there are things that are working today very good and practically. I wanted to mention that in terms of like having a better fairer assessment of where quantum technology is. First of all, quantum technology is not all quantum computing. Everything that uses laws of quantum physics is a quantum technology. For example, quantum sensors made by CSIRO, it's like at least for a decade, even more, that are being used by mining companies. That's the quantum technology, mature, being sold, solving a lot of problems, for example. And using machine learning on top of quantum simulation to extract information for things like drug discovery. It is being explored today and showing some results there. Some very specific mathematical problems that has some, this is like a mathematical term, group symmetries, but what it says that very specific problems that can be helpful for some, let's say, optimization tasks. In those specific one, quantum computers are showing better result than the classical one. There are some things that are not really happening soon. By soon, I mean not next year, but it might happen like 5 or 10 years. Quantum language models, this LLM AI that we have, we can't still put them on a quantum computer. Again, it's small. We don't have exactly figured out how to harness its full power and things like that. So still, we better having it on a normal computer. Molecular and material properties is very close, very good algorithms there, but still needs bigger devices to do it on big enough molecules to be impactful. For example, beating gradient boosted trees on tabular data is something that they haven't done yet, but it is very likely that they can do it. And yeah, broad quantum advantage claims, we don't have it yet. It's a very powerful machine. You have 100 qubits. You have 2 to the power of 100 numbers to save in there. That's huge. No, you cannot build a RAM on a normal computer that can save that. But also harnessing that is a huge challenge. So for sure, it breaks many paradigms that we have here, but there are challenges in harnessing that today. But yeah, very hopeful that we do it. So I share a peer review paper. This was done by my previous group at UQ. Professor Sally Shrapnel was my supervisor there. She has a PhD in quantum computing, also a medical doctor. So best combination of skills one should have for applications of quantum in digital health. So what they did, they looked at 169 paper, 82% used ideal situations to evaluate the result. Only 16 looked at noisy conditions. Noisy conditions means the current device that we have now. It doesn't mean that the ones that looked at the ideal ones aren't useful, because when we have fault tolerant, we have ideal. But it's not here today. So it's two kind of work. One is you're simulating it and showing that if I have ideal machine, I get these kind of results. Now we need to wait for the actual machine to do practical one. The other one, trying to harness something from what we have today. And between those, none of them really definitively showed better result than the classical one when you factor in every realities that you have, like for example, limitation number of qubits and the noise and everything. And there are some other technical problems that I want to go through, but these things all need like some classical optimization behind it. And unlike neural networks that we have like kind of back propagation, for those of you who are technical in machine learning, we don't have a back propagation for quantum algorithms. So it makes it really hard to tune those things to do a great job. But people are working on it. I'm very hopeful that very soon we can solve that. One result that shows promise today, that's one quantum enhanced stratification of breast cancers. This was a paper in quantum machine intelligence. On this dataset, Metabric, which has 1,980 samples of multi-omics breast cancer patients. And then they did clustering, like dividing that into different types of patients that you have there. So what they showed that is that if you want to match the expert clustering, like dividing those patients into groups that experts recognize as separate specific groups. If you try classical kernels, RBF kernels, we need 500 samples to reach 0.9 matching with expert clustering, but quantum kernel only needed 100. So this is something that we are focusing on now as well. When you don't have many data points, but you have a high dimensional data. This is a territory that almost every classical machine learning method, including neural nets, and also the more classical mathematical statistical based one, hit some problems. And yeah, quantum algorithms are showing some promise there, but this is like 5 times less data points. So there are many experiments in omics that you only have limited number of patients. If you want to learn from that, neural net needs like millions of data points, at least 10,000, I don't know, 100,000, preferably million. But you might only have like 100 or 200 or 500. So usually we fall back from those to more statistical ones, but now there is a second fallback that is better than even the statistical classical ones, and that's quantum kernels. So we are exploring that area. It is in the initial steps where we are doing there, but with University of Melbourne, we are exploring where we can apply this quantum machine learning methods into omics data and get some result there. Not exactly machine learning, but relevant applications that we are working on with QUT funded by Queensland government. We are working on quantum optimization for traffic. Specifically, this is for Queensland 2032. And we are working on currently electric bus scheduling for the games. So realistic routes that we have in Brisbane, and then finding the best way of sending these buses to different routes while considering, for example, the charging constraints and everything. And there is a huge, big machinery of optimization, multi-step iterations. And we are working on replacing one component with quantum optimization algorithm and keep the rest normal and overall get some better result there. So this is one of other applications of quantum computers is optimization, and a lot of financial companies and also transport companies are playing around with this. Again, we are limited to the number of qubits, or a specific algorithm needs the same number of qubits for the same number of buses. And we are now simulating 30 to 40 qubits. That's the number of buses that we can do. Ideally, we want 150 ideal qubits to do 150 buses. And then when you get to those numbers, 200, 300 buses, then no supercomputer can beat you, because it scales exponentially what they need to compete with a quantum computer in that arena. But at this point, with that 40, we can still somehow do it on a supercomputer. How much time? Yeah, still I do have a little bit of time. Quantum security. So I need to clarify this. Quantum security is that you, for example, send data using like photons in a quantum state to make sure that it's secure. This is not what I'm going to focus on now in this one. This is what focusing on what quantum computers break if you have big ones, and then what do we need to do about it. So one of the first very efficient quantum algorithm is called Shor algorithm. What it can do is, if you multiply two very big odd numbers, it can tell you what were those numbers in an efficient way. Normally, a normal computer needs to do a lot of trials, and with the 400 digit numbers that we use, it will take them a millennia to tell you what those numbers were. And if they tell you, then yes, you can break security on the internet. Means like encryption, when you encode a message, send it over internet to make sure that nobody can read it. When they look at it, it's just like a jumble of random numbers for them, unless you have a key to decrypt it back. But what they can, we don't have big enough quantum computers to break it today, but what can be done is that people can save those communications, and then when they have a big quantum computer in 5 or 10 years, start decrypting it. So it becomes a reality in a way in 5 or 10 years, but also it's a reality today because if you have a sensitive data, it's health data, financial sector data, some of them you don't want to be uh, exposed even 10 years from now. So you need to switch to something that quantum computer cannot break, and those exist. Specifically, some standard ones by NIST in the US that most people are focusing on to switch to. And what they do is they use different kinds of encryptions that even quantum computers cannot break. And for sensitive areas, we need to start like switching to those, which is a huge project, very costly. It is projected that US federal agencies will be spending 7 billion to move from current encryptions to post-quantum cryptography. Like Sash mentioned, this is another area that we are working with TAFE and some other national and state organization to create awareness and upskill people so that they have the skills to help this transition. One other project that we are working is a side project to federated learning project. Federated learning is when you have sensitive data, let's say at hospitals, you don't want to collect them all in one place because it's because of the privacy concerns. What you can do to train a model on them is that you send a copy of your model to all of them, where they are in the hospital, let's say. They learn a little bit from them, they come back, you do some kind of averaging, copy again, send back, and do it 100 times. And then you learn from all of them without moving that data or without the researchers who built the model seeing the data that they are training on. And what happens here is that the patient data, even the like an encrypted one, is not moving across nodes. So we might think that if we encrypt it and send it over, it's safe, nobody can see it. Only the researcher is the threat here. But with this quantum era threat, even if you encrypt it and send it, it is still vulnerable in the future, might be saved and used. So this is one way that federated learning adds to the security of patient data, and not the only way. It doesn't also expose it to the researcher, and it's not collected in one place so that one hacker can hack one computer and get access to patient data from 10 hospitals, let's say, and many other ways that it makes it a lot better for sensitive data. These are the things that we are working on: quantum transport, workforce readiness, and national investment in accelerating too. So most of you know about PsiQuantum, but more recently, Silicon Quantum Computing received like 60 million to expand their work. They're in Sydney. So it is a area that is growing, and it needs a little bit of patience, like AI. I mean, neural nets, we had it like a few decades ago. But for it to become what's today, even 5 years ago, people were skeptical if they can change anything in practice. There were like trials on some data, let's say medical data, which was promising and things like that. But this huge paradigm change by LLMs, when we had like big enough machines to run big enough models, suddenly changed everything. It's creating something that became so much efficient assistance that we cannot ignore anymore. So it's quantum technology, like specifically quantum computing, not technology. The technology in general, it is already, we have mature examples, but quantum computing still is in like 1970, 80 era of AI. But with so much money that governments and private companies are pouring into this, it will evolve a lot faster um, than a few decades. It will be in 5 or 10 years that we will see some big changes coming from this. But that said, it's not as widespread, the effect. You basically it is good at some algorithm, but not all. So it will work alongside normal computers. There are things that still normal computers do better, most of the things. And then if there is a specific problem like optimization or drug simulation or something like that, you send it over to your quantum processor, get the result, and continue with your normal. Yeah, sort of covered this before getting into this. Yeah, that was a snapshot of what QSIF is focused on, and more generally where the sector is and where Australia is heading. But I guess it's a good time for questions. Nana?
Yeah, so thank you. A couple of questions.
Yep.
The first one is around the reproducibility. Of course, there is a reproducibility crisis everywhere in science, and but my question to you is there something inherently limiting about quantum level reproducibility of computations? And uncertainty principle or whatever that might be playing a role in it.
Yes and no. By that, what I mean is there is this thing that when you encode a qubit somewhere between 0 and 1, and then you some operation, it ends up somewhere else. Each one of them end up in somewhere else in between 0 and 1. But when you actually look at them, each one of them, either they tell you I'm 1 or 0. If it's like 20% state is 20% 1 and 80% 0, and you look at it, there is an 80% chance that it tells you I am 0 and becomes 0 and stays 0, comes out of that superposition, and 20% chance that it tells you I'm 1. So if you're measuring at the end, each time you might get a different answer. And for a lot of algorithms, the solution is you need to run it multiple times, like let's say 1,000 times, and then look at statistic to see exactly where each qubit is. And then the more number of runs that you do, it gets better. So that final statistical answer is fixed and reproducible. Only if you want more certainty, you need to run it more. But
Sure.
the intermediate results are a bit random.
So the distribution is stable, but
Distribution is stable.
not a sample.
Yeah.
So it certainly makes sense. Yeah. So any algorithm you would devise should not be dependent on the intermediate samples or distributions.
No,
That's
what you do is you start from your, like, for example, let's say quantum ML, you input with usually a fixed encoding, translate that number 0 and 1 and something into something quantum, and then you have a kind of algorithms that is tunable. You need to train it and tune it, but after training and finding the good parameters, you keep the parameter fixed, and each time you send in the same data, you get the same kind of distribution at the end. So it is, in that sense, it is reproducible.
Sure. And the other one, of course, is related. You already said once you observe it, it crystallizes into some state.
Yeah.
And so is there an application for quantum memory? Of course, it will be unstable per se, but on the zero way,
It,
is it being
it is.
investigated? Yeah.
Yes, it is being investigated, and it will be very useful because sometimes you want to, for example, delay your actual quantum bit that is doing the computing might not be that stable. It might can keep there for 1 second, and sometimes you want to be able to keep it without looking at it, keep the same superposition for let's say 5 minutes until another calculation is done, and then you come back to this and use it. One thing that is directly people are doing is quantum encryption. When you send data on using photons in quantum state, for example, because you lose photon in a fiber after I don't know 60, 100 kilometers, you have a repeater, and quantum transmission cannot actually have a repeater. So you need to generate them and entangle them, and in there people are working on like quantum memories to enhance the distance that we can do with like quantum repeaters. That's one area, but in general, yeah, it's people working on quantum memory, more stable, yeah, quantum memories that you can save the quantum state in it and use it later.
Thank you, Moji. And
Sure.
Moji Insight is a great topic, and you made it very accessible.
Thank you.
Thanks, Nana. There's a couple of questions in the chat, Moji.
Okay, yeah, let me have a look. What's the optimal approach for integrating classical machine learning and neural networks with quantum computing, considering dataset size, computational complexity, and model performance and available quantum resources? Yeah, great point, Saha. We can mix them. One way we can do this is, for example, let's say I have a small quantum machine. It can only work on let's say 50 features, but my actual data set has like 10,000 features. One thing you can do is use your neural net as a feature translation from a high dimensional to a lower dimensional, then feed that into a quantum kernel and do, for example, clustering with that. Whether or not it's better than just leaving the clustering to the neural net, it's kind of a still open question. We haven't proved that this combination can do better. It's a relatively new thing, quantum machine learning, even compared to quantum optimization or cryptography is a lot older in the 90s and things like that. But people are working on it. But yeah, that's one way we can mix and match neural net with like quantum kernels.
I think there's another question from Mohammed as well. Mohammed, did you want to ask this one?
Yeah, thanks, Moji and Sasha. I think this is a really interesting topic and quite complex in my understanding the quantum theory. So I think, as you mentioned, Moji, in one of your slides about the testbed and rollout to the operational environment. So it's just like a kind of my impression that the rollout of the test beds will be quite crucial to have that lens of how these concepts will look like in the early stages, and giving that community more confidence on how we can roll out these early stage or early phase ideas into a more operational environment. So I think my point was more about the test beds that we have, like we are aiming to have in Australia, and one of the test beds that we have in UK, I think in previous weeks. Their role would be quite critical, I guess.
Yes, they are. It is very important, those kind of infrastructure, because you can directly work with the real system. It is very limited, the first version, only 5 qubits, but they made it the whole infrastructure that builds around it, those cooling and then translating into like web applications, is easily transferable to more qubits. And they have a rapid plan of making it more and more, but they decided to, even with 5, they decided to make it available, let the researchers play around with it. 5 means that you can trial a lot less number of samples or a smaller mathematical problem. Still, it might be good for people who wants to look at the role of noise, how they can limit that, and even for a small one, and then expand that to more number of qubits. But yeah, these kind of infrastructure are essential for quantum researchers in Australia, also those who are in industry and working on like startups should be able to have something real to play with. Okay, next question.
There was another question in the chat as well from Paul. If
Mhm.
you want to jump in, feel free to. And he said, I would like to ask what specific quantum frameworks and or hybrid algorithms should ECR in biomedical field prioritize learning today to prepare for the quantum era?
Yep. So there are two big like applications, optimization and machine learning. And for biomedical, I think more promising side is the machine learning side rather than optimization. For transport and logistic and financial sector, it's the other one mainly. But what's quantum algorithm? So in general, quantum kernels are very promising. And then we have like things that we call quantum neural nets, which there is a paper that says that these two are the same, quantum kernel, and you just approach it in 2 different ways. So underlying thing is the same. But yeah, if I want to point to one algorithm, quantum kernels to learn from data with low number of data points. So you need to look for where in the field there is, for example, this expensive sequencing happening, and then only you could do it and collect it from 100 patients rather than 1 million. And then you want to see how we can cluster it efficiently. Then yeah, we can trial things like quantum kernels to see how it does. But again, it's a young field, and if you like to, you can reach out to me through QSIF website. There's a contact us, and then we can just explore what's possible for your field.
Just a follow-up question.
Yeah.
If you could comment on the vanishing gradient problem with this neural net, that would
Yeah.
be good. Yeah, thanks.
So each machine learning models, there are numbers in there that needs to be tuned to match it to your data. Initially, you will start with some random numbers for let's say, for example, logistic regression. You have 10 columns in your data. You have 10 numbers, and you need to tune those numbers to something that matches your data, and it can do classification for you on your data. Neural net's the same. In that sense, it's not different. It might have million or billions, but still, there are some random numbers that you change it, and it can do, for example, cat versus dog classification on images. Before that, it randomly tells you this is cat, this is dog. Nothing better than picking random. But after you tune those numbers, and tuning those numbers, lots of numbers, if you don't have a good way of knowing which way to change them to get that result, it's an impossible combinatorial search for good numbers and continuous number too. But what's great about most of these ones, including neural network, logistic regression, and everything else, is that you have gradients. It shows you for each specific number that you can tune, it tells you in which direction and with which power you move a little bit to make the result a bit better. And you do it again and again, 100 times, 200, 1000. All of them will converge on some good numbers that can do cats versus dog for you. Unfortunately, quantum computers, because we can't look at the numbers that they currently saved in quantum state in there, we cannot have a gradient for the classical numbers that we have in there that we tune and we control that whole machinery. What we need to do is we need to regenerate that gradient with like getting 2 points and getting a bit mathematical, but getting 2 points and then look how much it changes between those 2 points. But it means that if you have 1 million, for example, parameters, you need to do 2 million operations to just figure out that gradient to do one step of 1000, and it's still not as good as analytical gradient. Backpropagation is the name of algorithm that does this in neural net. So we don't have that in quantum machine learning. And when the numbers get big, gradients become small, very close to zero. Even simulating that becomes a huge challenge. So this is one of the big challenges in both quantum optimization and quantum machine learning that needs to be fixed. But a lot of people are working on it, and I'm very hopeful that we can tame that problem, but at this point is one of the huge challenges. Yes.
Thank you, Moji. There was a couple more questions in the chat, but I know that we are at time, and I'm not sure if people need to go or if people want to hang on for a moment or two more. Moji, Sach, do you have a couple more minutes, or do you have to rush off at all?
I'm okay,
I
but
do not.
more than likely I can't answer anything, but that's okay. Emoji can stick around.
How much you hear? Ingrid, you had a great question. Are you still online? Yes, you are. Did you want to ask that one? Because there's a little bit of information there, but you can't see it.
Sure. It just so happens that I've just reviewed an open data journal submission, and it touched on this topic, so happy timing. But what I found really curious was about the really small scale of this data set. And I just wanted to understand a little bit more about why this choice. And I think you touched on it previously about honing in on some particular features. So I wondered if you could elaborate on that, because it was the use of kernels. And
Yes.
that was why I was quite surprised, because it was so small. And I understand that might be an element of not wasting compute. But I just wondered if you could elaborate a little on that.
It is small, because small is where the great neural networks that we love fail to give us results. And normally, yeah, because they have so many parameters to tune, having so many like low number of data points is a challenge for them to deal with. And before quantum computers, we used to use classic machine learning algorithms like kernels, like logistic regression, because, for example, logistic regression, there's assumption that the data is linear, and therefore it's easier to tune it and get some results. It won't be as good as if the relationship is not linear, it's so complicated. It won't be as good as a neural network what a neural network could reveal. But we can't use neural network anyway, because we don't have that many data points, so it struggles to learn. So this is the best that we can get. Classical, limited assumptions. And kernels, RBF kernels, classical kernels, are one way of not putting too much assumption in there, some kind of automatic translation between the initial space of let's say numbers that you have for these patients into something huge dimensional. Gaussian makes it huge dimensional, and in that huge dimensional, even putting a linear divide between them can reveal very good patterns. So a competitor now is quantum kernel. you can do it with a lot less qubits, very low number of qubits, and apparently with the result of that paper, you need 5 times less number of data points to get the same kind of clustering accuracy compared to RBF kernels. So it is the matter of showing that, yeah, these are data efficient. That's why a low number of data points becomes relevant, and that's why that paper focus on that specific one. And yeah, near term, we really need to look for those kind of applications to show something. But in the future, when we have enough number of qubits, we can trial these against neural nets on big problems as well. Lots of columns, lots of data points. At this point, they are not big enough so that we can translate a huge data set into something that, or a small quantum computers or the simulated ones on supercomputers can handle.
That's great, because I think there's a clear rule of thumb that people are working with there. And it also, I think, happily for those who are new to this, actually helps people think about breaking down the problem, like where your most pertinent challenges are. And this paper certainly touched on that. So I think there was a lot that was implied in that, and unpacking that for people who are trying to understand choices, for example, I think is really, really powerful. So thank you for the answer. That was great.
Sure. And in case in the future something comes up that might need like collaboration with QSIF, I just posted the link to our website, and just if you get in contact, we love to have a chat about these kind of projects.